In the previous video, we looked at how to construct search queries using the Materials Explorer app. In this video, we'll look at all the options available on the results table. So let me start by doing any search. So I'll pick lithium iron oxygen chemical space by elements. Okay, so here are some results for lithium iron oxides. Now, one of the first options is to change the amount of records we see on a page, because there's actually 115 search results, but we only see 10. So for example, if I want to see more results, I could change this to 25 or 50. One of the next things that you can do is this batch and edit structures, and what these buttons allow you to do is to send some of these structures to the Crystal Toolkit app, which allows you to edit those structures and change atom positions or change elements that are in the structure. And it allows you to browse their crystal structures. So for example, let's say I pick 3 of these structures and I click Edit. This brings me to the Crystal Toolkit app, where there's multiple operations that I can perform on these structures. For example, create supercells. We'll do a separate tutorial video on Crystal Toolkit at some point. For now, just notice that you can actually switch between these 3 structures and it will show their crystal structures. So that's one way that you can actually browse the crystal structures of the results very quickly. Let's go back to those results. Now by default, the results table shows several columns of properties for the materials. But actually there are some more options in the Show Hide Columns button. So if I click that, I'll see, for example, that I can get additional properties of the materials. For example, this has band structure tells me whether we've computed a full high-quality band structure object or whether we've only done a structure relaxation calculation. So for example, let me click this button and see what happens. So now we can see that the results table has this has band structure column, which is true for some of the entries, which means we've actually computed the full band structure, and false for the others, which means that we haven't computed a high quality band structure. Notice for the ones that has false, it actually, for the band gap, gives a warning saying that we actually have only computed this gap using a loose K-point mesh from the structure relaxation run, and we don't have a fine mesh for which to derive the band gap. For now, I'll hide the has band structure. Now, if I like the results on this page and I want to bring it, let's say, to Excel or to another application, I can, for example, copy the results. So let me click Copy. And now this has copied all 115 results to the clipboard. Now let's say I open up a text editing application and I paste the result. I now have all 115 results in a tab delimited format that I can import or export to other programs. There's also native options to export to certain formats, for example CSV and Excel. The column headers for the results table are actually sortable. So for example, if you want to put the densest materials first or last, you can click the density column and it'll start sorting the materials by density. And if you click it again, it sorts in the reverse way. Finally, the last thing to keep in mind is that everything reported here is a computed value with density functional theory, and the values might not be the same as experiments. In particular, the band gap is severely underestimated with regard to experimental data. You can get more information about how accurate these calculations are in the tutorial for the details page, which shows you how to see help guides for these different properties, and also in the documentation. In particular, the documentation for the calculations guide has more information about the accuracy of these calculations.